Good morning everyone, I am Ayan Kenneth Timonterde and I will be discussing about pressure measurements and flow measurements. Let's start first with the pressure measurements. What is pressure? Pressure is the force per unit area. It is usually expressed in terms of familiar units of weight, force, and area, or the height of a column of liquid which produces a like pressure at its base. We have three groups or methods for devices measuring the pressure. We have the height of a liquid column, distortion of an elastic pressure chamber, and the third, the electrical sensing devices. Now, let's have the first method for pressure measuring devices, which is the liquid column methods. In this method, pressure being measured is balanced against the pressure exerted by a column of liquid. If the density of the liquid is known, the height of the liquid column is a measure of the pressure. The most common device for this method is the manometer. So this is what the manometer looks like, as you can see in the diagram presented in your screen right now. The yellow one inside the U-tube can be either mercury or water. So that's the two most common liquids used in manometer. We have a formula for manometer, if you can still remember, which is delta P is equal to the difference in densities times gravity times height. For the second method, we have the elastic element method. Under this method, we have three classified groups, which are the Bourdon tube, bellows, and diaphragm. In this method, the measured pressure deforms some elastic material, usually metallic, within its elastic limit, the magnitude of the deformation being approximately proportional to the applied pressure. Let's discuss now the three groups. First, we have the Bourdon tube elements. In this device, materials are selected on the basis of pressure range, resistance to corrosion by the process materials, and effect of temperature on calibration. The most often utilized equipment for this is the C-spring Bourdon tube pressure gauge. So this is the illustration for the Bourdon tube pressure gauge. We have the different parts of it. We have the pointer, Bourdon tube, end of tube, link, sector gear, movement, socket, and process media. So the water will flow through the process media and it will make the Bourdon tube deflex, and the pointer will move clockwise as it measures the pressure. So to understand better its mechanism, let's watch this video.
Bourdon tube pressure gauge. Bourdon tube pressure gauges are used for the pressure measurement of relative pressure from 0.6 bar to 7,000 bars. They are classified as mechanical pressure measuring instruments and thus operate without any electric power. This video will cover the followings. 1. Working principle of Bourdon tube pressure gauge. 2. Construction. 3. Working. 4. Advantages and disadvantages. If you are new to ADTW, click on the subscribe button below and turn on the notification to get all the updates from our channel. Working principle of Bourdon tube pressure gauge. When an elastic transducer, such as Bourdon tube in this case, is subjected to a pressure, it deflects. This deflection is proportional to the applied pressure when calibrated. Construction. A C-type Bourdon tube consists of a long thin-walled cylinder of non-circular cross-section, which is sealed at one end. This tube is made from materials such as phosphor bronze, steel, and beryllium copper, and attached by a light mechanism which operates the pointer. The other end of the tube is fixed and is open for the application of the pressure, which is to be measured. The tube is soldered or welded to a socket at the base through which the fluid, whose pressure is to be measured, enters the C-type Bourdon tube. Working of Bourdon tube pressure gauge. As the fluid under pressure enters the Bourdon tube, it tries to change the cross-section of the tube from oval to circular, and this tends to straighten out the tube. The tip of the Bourdon tube is connected to a segmental liver through an adjustable link. The segmental liver end on the segment side is provided with a rack which meshes to a suitable pinion mounted on a spindle. The segmental liver is suitably pivoted and the spindle holds the pointer. The resulting movement of the free end of the tube causes the pointer to move over the scale. In real-life application, the pressure gauges are mounted with siphon tube. Siphon tube is a simple device used to protect a pressure sensor from high-temperature media, such as steam. It can also be used to reduce the potentially damaging effects of rapid pressure changes. When first installed, the siphon should be filled with water or some other suitable separating medium. This medium continuously remains in contact with the Burden tube.
So that's the mechanism of the Bourdon tube pressure gauge.
Burden
Let's proceed to the second group, which is the bellows element. So it is an actually elastic cylinder with deep folds or convolutions. The pressure to be measured may be applied either to the inside or to the space outside the bellows, with the other side exposed to the atmospheric pressure. For measurement of absolute pressure, either the inside or the space outside of the bellows can be evacuated and sealed. Differential pressures may be measured by applying the pressure to the opposite sides of a single bellows or to the two opposing bellows. So this is what a bellow pressure looks like. So we have here A, the spring, the B, the pointer, and C, where the water flows through the pressure gauge. So to understand and have a more comprehensive explanation of its mechanism, let's watch this video.
Bellow pressure gauge. Do you know how we can measure the pressure of flow of water in a peaceful river? Actually, there are many instruments by which we can measure the pressure of flow. One of the instruments that we can use to measure the pressure of flow is bellow pressure gauge. Now let's see the working of bellow pressure gauge in the animation. As we start the water supply in the pipeline, the water strikes the tubular membranes known as bellow. Then the pressure to be measured is applied outside the bellows. A bellow gauge contains an elastic element, that is spring, that is a convoluted unit that expands and contracts axially with changes in pressure. The spring in bellows gauges is made of brass, phosphor bronze, stainless steel, or other metal that is suitable for the intended purpose of the gauge. The movement of the bellows can be converted into linear displacement. This displacement can be converted in terms of pressure. As flow of pressure increases, a pointer starts rotating on the dial, which indicates the pressure of the flow. And to make this measurement precise, the scale of the dial is divided in many sectors. After some time, the pointer assumes a new position on the pressure calibrated scale on the dial to indicate the applied pressure directly, and thus pressure is measured on the dial.
So that's the mechanism of our bellow pressure gauge. Let's proceed to the third and last type of the elastic element method, which is the diaphragm element. So it has two types. First, it uses the elastic properties of diaphragm, which are recommended for high pressure. The second one, opposed by a spring or other separate elastic element, and it is good for extremely low pressure, vacuum, or differential pressure. So for the first type, it is usually consists of one or more capsules, each composed of two diaphragms bonded together by soldering, brazing, or welding. For the second type, it is used for containing the pressure and exerting a force on the opposing elastic element. The diaphragm is a flexible or slack diaphragm of rubber, leather, impregnated fabric, or plastic. So this is an illustration of diaphragm pressure gauge. And to understand its mechanism, let's watch this video. And in this video, it compares the Bourdon tube and the diaphragm element.
In industrial measurement technology, two different types of pressure gauges are used: Borden tube pressure gauges and diaphragm pressure gauges. They have different operating principles and are therefore suitable for different applications. With Borden tube pressure gauges, the pressure is measured by a Borden tube transmitting pressure directly to the pointer. Borden tube pressure gauges can be used in a variety of applications and cover the majority of applications. However, when Borden tube pressure gauges reach their limits, then diaphragm pressure gauges are used. In diaphragm pressure gauges, the pressure is transmitted via a wave-shaped diaphragm to a link. This then transfers the pressure to the movement. Diaphragm pressure gauges show their strengths, for example, when measuring low pressures. Due to the large diaphragm surface, measuring ranges from 16 millibar are possible. For a Borden tube pressure gauge, on the other hand, the smallest measuring range is 600 millibar. Diaphragm pressure gauges offer good protection against overload since the diaphragm can support itself against the upper flange. Vica diaphragm pressure gauges offer 5 times the overload protection as standard ones. Optionally, even much higher overload safeties can be realized. Diaphragm pressure gauges also have advantages when used with critical media. The diaphragm element can be coated with a variety of materials such as PTFE, gold, Hastelloy, and many others. This protects the instrument from aggressive media. Optionally, the lower flange can also be lined with special material. Diaphragm elements with open connecting flange are also suitable for viscous media. Due to the large cross-section of the pressure port, this cannot clog. The decision for Borden tube or diaphragm pressure gauges thus always depends on the specific application. Here at Vica, we are happy to advise you on the right choice of pressure gauge for your application.
So that's the mechanism of diaphragm element and how it differs from Borden tube. Since we're done discussing about the liquid column methods and elastic element method, let's proceed to the last method, which is the electrical method. So most devices belong to this method utilize electricity. It is divided into 3. We have the strain gauges, piezoresistive transducers, and piezoelectric transducers. First device under electrical method is the strain gauge. So strain gauge are devices utilizing resistance wire grids for measuring small distortions in elastically stressed materials. The resistance is resulted from the increase of wire length and decreased in diameter. Strain gauge pressure are made in many forms for measuring gauge, absolute and differential pressures, and vacuum. So it has 2 basic forms. We have the bonded and unbonded. For bonded form of strain gauges, this device bonded directly to the surface of the elastic element whose strain is to be measured. Unbonded strain gauges consist of a fixed frame and an armature that moves with respect to the frame in response to the measured pressure. So this is a diagram for a strain gauge. As you can see, we have here the strain gauge, the diaphragm, V out, and the V excitation, and the applied pressure. To fully comprehend its principle, let's watch this video.
In this media, you are going to learn to find the unknown pressure of a gas or fluid using resistive strain gauge. It consists of a capsule divided by a membrane, long resistor strip XY, and Wheatstone bridge. Wheatstone bridge is used to find changes in resistance of the resistor strip. Among 4 resistors in Wheatstone bridge, one is this resistor strip. This resistor strip XY is connected to the center of the membrane. In that point, X is fixed and Y is movable. One side of the capsule is filled with the fluid of known pressure and the other side is filled with the fluid of unknown pressure. The pressure difference of 2 fluids inside the capsule causes membrane deflection in one side. Due to this membrane deflection, the resistor strip is stretched out from XY to XY'. This stretching causes a reduction of area of cross-section of the strip and increases its length. Hence, the resistance value of the strip increases. This change in resistance causes unbalance in the bridge and shows indication in the voltmeter. This resistance can be determined using voltmeter value. From that, unknown pressure can be calculated.
So that's the mechanism and ways on how to compute pressure using resistive strain gauge. The second device under electrical method is the piezoresistive transducers. So it uses the piezoresistive effect to convert physical quantities to electrical quantities. It is also utilized when a change in mechanical input in a structure needs to be measured. The principal advantage of piezoresistive transducers are a much higher bridge voltage output and smaller size. So this is the illustration of the piezoresistive transducer. So we have here the pressure 1 and the pressure 2, the silicon diaphragm, the resistor, of course, and the contact. To know more about its principle, let's watch this video.
Hi, I'm Clint. Welcome to Automate. In this video, I'm going to simplify and explain piezoresistive pressure sensors. Since the introduction of electronic control over fuel and ignition systems, pressure measurement has been required. Most early systems used a mechanical pressure sensor consisting of a diaphragm connected to a potentiometer. As the diaphragm moved due to the pressure change, so did the resistance value of the potentiometer. These older type sensors are not suitable for modern vehicle electronic signals as they are too slow and imprecise. The sensing material in a piezoresistive strain gauge is a diaphragm formed on a piezo silicon substrate which flexes with applied positive or negative pressure. When flexing, the substrate material deforms, causing a change in the structure of the piezo crystals. This change in structure results in a resistance change in the material. I hope you're enjoying this training video. Any technician working in our industry today must have the very best training just to keep up to date. Isn't it time you got started? Simply go to our website now.
So that's the piezoresistive transducers. Let's proceed to the last device. Which is the piezoelectric transducers. So piezoelectric transducers generate a potential difference proportional to a pressure generated stress. It offers high electrical impedance and that's suitable for measurement for static process pressures. So this is the illustration for piezoelectric transducers. So we have here the force, the electrodes, the piezoelectric transducer, and its output voltage. To understand this one better, let's have this video.
Here is a functional diagram, pictorial diagram, of a device called a piezoelectric transducer. What it does is it converts sound waves into an electrical audio signal, or vice versa. In effect, it can serve as a microphone or as a loudspeaker. The way that it works is you place two metal plates, one on either side of a piezoelectric sample. Piezoelectric meaning something like quartz, as you would find in a quartz crystal. Maybe these at radio frequencies are commonly used for signal generation in oscillators. But you can also use them in audio applications as microphones or speakers. When acoustic waves encounter these metal plates and vibrate them, the piezoelectric material vibrates and creates a signal that's identical to the acoustic signal that comes in, except it's an electrical signal. Conversely, if you apply an electrical signal to these plates, what you'll get out is acoustic waves that sound just like the electrical signal that went in. So you could use it as a speaker or a microphone, or anything else. You could any other audio application where you want to convert sound waves to electrical audio signals.
So that's the application or mechanism of the piezoelectric transducers. The next topic is about flow measurements. There are some devices here that are familiar to us since we encountered them during our momentum transfer course. Now, let's have a run through of the devices that measures the flow. But before that, what is flow? Flow is the volume per unit of time at specified temperature and pressure. So by definition, it is the volumetric flow rate. However, there are also other types of flow such as molar flow rate and mass flow rate. Flow is measured by either positive displacement or rate meter. Positive displacement can be used when the flow is divided into isolated measured volumes, while rate meter applies to all types of flow meters through which the material passes without being divided into isolated quantities. Let's proceed to the first type of flow meter. We have the orifice meter. Orifice meter is a square edge or sharp edge orifice and a clean-cut square edge hole with straight walls perpendicular to the flat upstream face of a thin plate placed crosswise of a channel. The most widely used flow meter involves placing a fixed area flow restriction, an orifice, in the pipe carrying the fluid. This flow restriction causes a pressure drop which can be related to the flow rate. Additionally, the most widely used flow meter involves placing a fixed area of a flow restriction or an orifice. So you can read more about the orifice meter in the section 10-16 on the 8th edition of Perry's Handbook. So this is what an orifice looks like. So we have here the diameter 1 where the flow passes through, and D2 the diameter 2, and there is a change. Since there is a change in the diameter, so there is also a change in the pressure, and by then you can calculate now the flow of the fluid. So we have here the formula for our flow rate. So we have Q sub A is equal to the coefficient times the area over square root of 1 minus area 2 over area 1 squared multiplied to the square root of 2 times the differences in pressure all over the density of our fluid. So the next type is the Venturi meter. So this flow meter has the same mechanism with the orifice. However, discharge coefficients of Venturi are larger compared to orifice. Then, the standard Herschel type Venturi meter consists of a short length of straight tubing connected at either end to the pipeline by conical sections. Venturi tube operates on exactly the same principle as the orifice. So you can read more about the Venturi meter in the section 10-18 of 8th edition Perry's Handbook. So this is what a Venturi meter looks like, as you can see in the diagram on the left side. The third flow meter is the rotameter. So rotameter, for a given flow rate, the float remains stationary because the vertical forces of differential pressures, gravity, viscosity, and buoyancy are balanced. The float position is the output of the meter. So you can read more about the rotameter in the section 10-20 of Perry's Handbook 8th edition. So we have here the different parts of the rotameter. As you can see in the diagram, the left, we have here the outlet, the stuffing box tightened from outside here with Angus screwdriver, the stuffing box packing, stuffing box follower, the bar nut to tighten stuffing box, and etc. Next, we have the turbine meter. If a turbine wheel is placed in a pipe containing a flowing fluid, its rotary speed depends on the flow rate of the fluid. A turbine can be designed whose speed varies linearly with flow rate. Then, the speed can be measured accurately by counting the rate at which turbine blades pass a given point using a magnetic pickup to produce voltage pulses. Means are provided for magnetic detection of the rotational speed, which is proportional to the volumetric flow rate. So you can read more about the turbine meter in section 10-21 of the 8th ed. Paris Handbook. The fifth one is the vortex shedding flow meter. So these flow meters take advantage of vortex shedding, which occurs when a fluid flows past a non-streamlined object, a blunt body. This flow meter is recommended for use with relatively clean, low viscosity liquids, gases, and vapors, and rangeability of 10:1 and 20:1 is typical. So here's the diagram, the illustration of a vortex shedding flow meter. Accuracy can be also maintained regardless of density, viscosity, temperature, or pressure when the Reynolds number is greater than 10,000. After vortex shedding flow meter, we have the ultrasonic flow meter. So it has two fundamental techniques in measuring. We have the two opposing transducers are inserted in a pipe, and second, flowing fluid must contain scatters in the form of particles or bubbles which will reflect the sound waves. So ultrasonic flow meters are based upon the variable time delays of received sound waves which arise when a flowing liquid's rate of flow is varied. So for the first fundamental measurement technique, these transducers are then used to measure the difference between the velocity at which the sound travels with the direction of flow and the velocity at which it travels against the direction of flow. For the second fundamental measurement technique, these scatters should be traveling at the velocity of the liquid. A Doppler method is applied by transmitting sound waves along the flow path and measuring the frequency shift. Next, we have the magnetic flow meters. Magnetic flow meters follows the principle of Faraday's law of electromagnetic inductance. A minimum value of fluid conductivity is required to make this approach viable. The pressure of multiple phases or undissolved solids can affect the accuracy of the measurement if the velocity of the phases are different from that for a straight run pipe. Magnetic or magmeters are very accurate over wide flow range and are especially accurate at low flow rates. Typical applications include metering viscous fluids, slurries, or highly corrosive chemicals. So this is the diagram for a magnetic flow meter. So you can see there is really a magnet there, since that's the basic principle of the magnetic flow meters. Next up, we have the Coriolis mass flow meters. It utilizes a vibrating tube in which Coriolis acceleration of a fluid in a flow loop can be created and measured. They can be used with virtually any liquid and are extremely insensitive to operating conditions, with pressure ranges over 100 to 1. These meters are more expensive than volumetric meters and range in size from 1/16 to 6 inches. So that's the diagram for Coriolis mass flow meter. So we have here the input, and it will travel down to the tubes that will pass through the sensors and the oscillating drive and will exit through the output. The last type of flow meter is the thermal mass flow meters. They are widely used in semiconductor manufacturing and in bioprocessing for control of low flow rates, called mass flow controllers or MFCs. MFCs measure the heat loss from a heated element which varies with flow rate. Capacitance probes measure the dielectric constant of the fluid and are useful for flow measurements of slurries and other two-phase flows. So to summarize everything about flow meters, let's watch this video.